We have with us Dr. Ananya Ghosh Dastidar. Ma'am is presently Associate Professor in the Department of Business Economics, South Campus, University of Delhi. She has completed her MA, MPhil, PhD from CESP, JNU, New Delhi. She has a teaching and research experience of more than 20 years. Her areas of research and teaching include international economics, economics of development, in particular, the problems of poverty and income inequality in developing countries. Her subject expertise is in areas of macroeconomics, e- econometric methodology, and Indian economics. She has contributed a number of research articles in various Indian and international journals, and she has few research based books to her credit. She has guided a number of research students. It's an honor and privilege to have you, ma'am. Thank you, ma'am. Over to you, ma'am.
Thank you, ma'am.
Okay, thank you. So I hope all of you can see my slides.
Ma'am, your slides are visible, you are audible, and you are also visible. Thank you, ma'am.
So as the title suggests, today's session is going to be an introduction to the simple ordinary least squares regression model. Let's proceed. So what we will discuss today is listed over here. As I said, we'll start with an introduction where initially we will be viewing the data, then we will be going on to understand the meaning of the regression line. As you can see, the touch points of today's discussion have been highlighted in red on this slide. So after viewing the data and understanding the meaning of the regression line, we'll move on to some technical details, which involve a deeper understanding of the regression model. So we will go through the model assumptions. We will look at model predictions, residuals, understand some of the results that are displayed when you run a standard ordinary least squares regression, such as R squared. Understand how to carry out hypothesis tests, which would involve understanding terms like standard errors, t-statistics, p-values, so on, and then move on to interpretation of estimated coefficients in the two-variable model. We look at different examples, and we will also be running regressions in Excel. So I will get you started and you will be running those regressions. So what I want to stress over here, as you can see, today we will have a lot of understanding to do. Okay, so let's move on. So what is ordinary least squares regression all about? Understanding that is linked to remembering something we did a very long time ago in school. We learned about straight lines, right? So that's where we begin from. We begin with straight lines as we ask, so what is ordinary least squares regression all about? Okay, so we are talking about a two-variable model. So a simple two-variable model involves one dependent variable and one explanatory or independent variable. Okay, so I'll just come in a minute to what these dependent variable, explanatory variables, etc. are. All right. I have seen the kind of things you've been covering in the workshop so far, so I'm assuming that you know exactly what a variable is, right? So a variable is not a constant. Remember, it takes different values. And in the two-variable model, we are dealing with two variables, as I said, dependent and either independent or explanatory variable. Right. Now, remember, we are going to talk about what OLS regression is all about. And a lot of it has to do with estimating a straight line. Okay. What kind of a straight line? A straight line relation between the two. between the dependent variable and the independent variable. That's what ordinary least squares regression is all about. Now, before I proceed any further, let me just make sure you remember all that I want you to remember about straight lines, okay? So we'll start with the equation of a straight line. This is the standard way in which we write the equation, okay? So we have two variables, y and x. And if there is a straight line relation between the two, we write y is equal to mx plus c, or y is equal to c plus mx. What is c? Now this is in blue, right? So remember the color. The c is blue, the m is red, okay? So c is the intercept and m is the slope of our straight line. First thing to remember. Now, some more about straight lines. From very basic calculus, remember that the slope of the straight line is what is captured by dy dx, okay? So my equation is y is equal to mx plus c, right? Where the slope m, all right, is basically dy dx. So how do we interpret the slope m? It represents the change in y. So m is the amount of change in y for a small change in x. That's how we interpret slopes, right? So if I say, so starting with, hang on. So starting with dy dx is equal to m. If dx is equal to 1, then dy is equal to m, right? So basically, we can say that m measures the change in y for a unit change in x. Okay. So I'll just repeat what I just said. So what am I discussing here? Sorry. So I'm discussing what OLS regression is all about. It's all about estimating, okay? It's all about estimating a straight line relation between two variables, one of which is a dependent variable and the other one an independent variable. Now, once we have such a straight line, what are we going to have? We are going to have essentially an intercept and a slope, right? And what does that mean? What is it that you have when you have the estimate of a slope? That's the next thing to remember. So when we have a slope, we basically have a number m, which captures for a unit change in x. So if x changes by 1 unit, remember x is my explanatory variable. So if the explanatory variable changes by 1 unit, what is the amount of change in my dependent variable, which is y? Right? That's what ordinary least squares regression is all about. It's all about getting an idea of how your dependent variable changes when your explanatory variable changes just a little bit. Okay. So now let's look at some data. Remember I said we're going to view the data. So let's view some data and let's see what dependent and explanatory variables may be looking like. So here we go. Right. So let's first look at the left side of the screen where I have a variable called wage. And here I have a variable called edu. So what is wage? Wage is hourly wages, okay? And these are measured in dollars. And what about edu? Edu is years of education, all right? So you have these two variables which are giving you for a group of people, right? So I have 30 observations, 30 or so observations over here. And which means that for 30 people, I have what is their hourly wage and how many years of education do they have, right? So implicit here is a dependent variable and an explanatory variable. My implicit assumption when I show you this data is to say that, look, how much a person earns, what their wages are, depends on how educated they are. Okay, that's my implicit assumption. In fact, I'll go beyond that and I'll say I expect that the more educated a person is, the higher would be the amount he expects to earn every per hour. Okay, so hourly wages would be higher for people with a higher amount of education. Okay, so I have with me two variables. I have a dependent variable. So this is my dependent variable and this is my explanatory variable. Okay, or you can call it the independent variable as well. Now, remember I told you that what regression is all about it's all about estimating a straight line relation between wage and education. It's all about estimating a straight line relation between the dependent variable and the explanatory variable, right? So when you run a regression, you actually end up with something like this, okay? So let's have a look at what we end up with when we have actually run such a regression. We end up with something like this. Now here is my color coding. Remember, intercept in blue, slope in red, right? So when I have a straight line relation between wage and education, and it reads like this: wages is equal to 0.09 plus 5.4 edu, right? It's saying that, look, as education increases, if you were to say that wages are also going to increase, and if you were to draw a straight line to capture that, then the slope of that straight line is 5.4 and the intercept of that straight line is 0.09, right? Now, we just discussed what a slope means. So let's see what the slope means over here. It means that for one more year of education, okay, a person's wage is going to increase by $5.4. Okay. Now, where am I getting this from? I'm just getting this from the fact that dy dx is equal to 5.4 over here. Dy dx is the slope of a line. In this case, the slope of the line is 5.4. Okay, so look at this line and equate it with the equation of a straight line. Y is equal to mx plus c. So what is y over here? Y is wage, right? Can you hear me? Am I audible? Because I think the internet. Okay, fine. It just gave me a message saying the internet connection is not good. Right. So, so Y is wage and X is education. Keeping that in mind, look at this equation, okay? It is saying Y wages is equal to MX, all right? So M is 5.4 and C is 0.09 and X, of course, is education, right? Okay. So therefore, when I ask this question, what is this line saying about the relation between wages and years of education. Let's just understand that by using our basic understanding of straight lines. It is saying that in case education, so basically it is saying that in this case, dy dx is equal to m, it is equal to 5.4, which is as education increases by one more year, wage will increase by $5.4. How can I say all of this? Because I know the units in which these variables have been measured. I've told you that, okay? Right. So you're wondering, of course, that how did we estimate? How did we estimate the slope and intercept in the first place? Well, we used OLS regression. And how does that work? That's exactly what we are going to see. Okay. So before I proceed to OLS regression and how we get into all of this, I'm going to take you through two more examples exactly like this. So I'm going to show you two more pairs of dependent, independent variables. And we're going to look at these lines and we're going to interpret the coefficients, right? And then we'll come to the model, its assumptions, etc. So what I'll be doing is I'll take you through these two more examples and then I'm going to pause and I'm going to take questions, if any, regarding straight lines. So the only questions I'm going to take at this stage are going to be on straight lines that we are discussing, okay? So if you have any questions following my discussion on dependent variables, explanatory variables, if I get a straight line, how do I interpret that straight line? Okay, that's what I'm going to take. How you estimate the straight line, I will come to. So right now, when I pause, I will not take questions on how to get that straight line. Is that clear? Okay, let me carry on. Now here you have a different set of dependent and explanatory variables. Here you have the dependent variable, which is normally denoted as y, as price. Price of what? Well, this is a data set on house price. So house prices measured in thousands of dollars. And what is my explanatory variable? The x variable is size. Okay. So size is measured in square meters. So what is the implicit assumption? The implicit assumption is that the size, the price of a house measured in dollars is a function of how big it is. Okay, its size in square meters. Okay. So what I want to say here is, what is my dependent variable? What is my explanatory variable? These issues come from the context. Okay, you have to have some theory. You have to have some training in a particular field. Okay, when you are actually using regression. So what you have in mind when you are using regression is, so here's this variable y, which depends on another variable x, and I really want to find out if there is a straight line capturing the relation between y and x, what is the intercept of that straight line? What is the slope of that straight line? Okay. And why do we want to say that? We want to say that because end of the day, we want to figure out, so if my explanatory variable changes a little, how does the dependent variable respond? Okay. So this data, when it was used to estimate a regression line, we got something like this. Okay, y is equal to okay, mx plus c. Remember, so m over here is 0.12. Look at the color. The slope is in red and the intercept is in blue. Okay, so c is 44.9. Now, mostly intercepts don't have very interesting interpretations in two variable regression models. Sure, they're telling us something. They're saying that if x is 0, then what is y? in this case, that's saying if size is 0, then what is the price of a house? Now, that doesn't make sense, right? So mostly, the question that the intercept is answering is not something that we're very interested in asking, certainly in two variable models, which is not to say that intercepts are not important. They're important. They're giving the position of the line. So if you have an axis where you have X over here and Y over here, so the intercept tells you whether it's a line like this or whether it's a line like this, right? So this has a very small intercept. This has a much larger intercept. So intercepts play an important role, but mostly when it comes to interpreting them, we are not that interested, okay? So here, given that I've told you the units in which the two variables are measured, price in $1,000, size in square meters, what is this saying? This is saying that for 1 square meter increase in house price, for 1 square meter increase in size, the price of a house will increase by $0.12,000. Why $1,000? Because that's the unit in which house price is measured. So if size increases by 1 square meter, house price will increase by 0.12 into 1,000, which is equal to $120. Okay, that's what this is saying. And how do I know that? It's just coming from my basic interpretation of the slope of a straight line. That's the simple point that I want you to get at this stage. Because how we estimated this line and how it works, we are going to go on and see that just in a minute. One more example and then I'll take questions. So this is a data set, which again is a cross-section data set. So we'll come to what are cross-section data sets and so on. So this is a data set which tells you for 30 firms, what is the salary of the CEO, okay? This is CEO salary in not hourly wages, sorry, it's CEO salaries in $1,000, and so the CEO salary is my dependent variable over here, and ROE is return on equity. So the implicit assumption here is how much the CEO of a firm gets paid depends on firm performance. In this case, we are saying the financial performance of the firm as reflected in its return on equity. I have to give you the units in which variables are measured. So the CEO salaries are measured in $1,000 and ROE is measured as a percentage, okay? Now, when I run regression, remember I estimate a straight line relation between my dependent variable, which is CEO salaries in this case, and ROE, which is my explanatory or independent variable. I get this kind of a straight line, where now M is 18.5. What is this saying? It's saying that if ROE were to increase by 1 percentage point, the CEO salary would increase by 18.5 into $1,000. That's $18500. Okay, that's how you interpret regression lines. And the point is understanding straight lines and how to interpret slopes is going to be very important as we go ahead. So let me pause here and see if you have any questions. I can see some questions, so I'll just have a look, and I will Right. Yeah. So if anybody has any questions, you could just raise it
Purushottam sir,
on.
Purushottam sir, please allow the chat box.
Yes, yes, I'm allowing the chat box.
Ma'am,
Please
do
go
you
ahead.
also want to the live questions to be taken by raising the hands?
Uh, sure. I prefer a chat because I've never done that. So maybe I could do that at the end. So right now, if you have a
Sure, ma'am.
question, you could just type it. Okay. So
Ma'am, the
right.
questions have started pouring in.
Yeah. Yeah. So okay. So
Yeah, should I
Dr.
repeat?
Pandey is asking how to calculate C and M. I'm going to come to that, Dr. Pandey. What about Azra is asking what is the intercept? Okay, Azra, I'll just touch on that briefly. And Dr. Yadav is asking the definition of a dynamical variable. I haven't talked about dynamical variables, so I'm not going to take that now. Right. So Dr. Srinivas Rao is wanting a book. I'll come to books at the end. So the only question I respond to now is what is an intercept? The difference between log linear models and logistic regressions we will touch on tomorrow. So I'm not answering that right now. So let me just look at what is an intercept and then I will carry on. So, okay. So I'll just draw an axis over here on my screen. So when I have X on my horizontal axis and Y on my vertical axis, and I'm plotting a straight line of the form mx plus c. C is the intercept. So C is the point at which so C is the point at which so yeah. So C is the point at ouch. I just turned that into a pen. Okay, so this is not quite a straight line, but anyhow. So this is the intercept, okay? This is C. So the point where the line cuts the axis, right? So you can see when X is equal to 0, right? That's when the line cuts the axis, right? Y is equal to C, all right? It is the value of your dependent variable when the explanatory variable is 0. That's what C is, all right? Okay, and Dr. Pandey, I'm going on to how you get C and so on, all right? I'll have a quick look to see if there are any other questions that, what is slope and intercept? Yeah, right. So I'll just run through this once again, the concept of the slope and the intercept, okay? Okay. So I'll just give me a moment. So I'll just yeah. So yeah. Okay. So now I'm going to explain what a slope and an intercept is in the context of a straight line. Believe you me, this is fundamental to an understanding of results once you have run a simple regression model. So when I have a straight line of the form y is equal to mx plus c, and I plot it, look at what I have on my axis. On the horizontal axis, I have x, which, as I said, is my explanatory variable. On the vertical axis, I have y, which is the dependent variable in a regression model. Now, when I have a straight line like this, okay, just one second. Let me try and draw a better straight line than this. Okay. Yeah. So, okay. Yeah, it's not very straight, but please assume that it's straight, okay? So when I have a straight line like this, what I have is, this represents mx plus c, all right? What is c? This is c. This is the intercept. What is slope? This is the slope, right? So you could think of two lines which have the same intercept, but which have different slopes. So here's another line, okay? So let's say this is one in y1. This is another line, okay, which is m1x plus c is equal to y2. So y is being measured here, and these are the this is the slope, and that's the intercept. So when we are using regression to estimate the relation between two variables, we are essentially estimating a slope and an intercept, which represents this relation. Okay. So let me proceed, and I will take questions a little later. Otherwise, we are not going to cover the ground I had planned. And if you still have basic questions about straight line, you'll just have to get back and just revise this concept later today, so that you clear all your doubts. Okay, so I'll come back to questions at the end. Now let me proceed to tell you how to estimate this slope and the intercept. Okay, right. So let me come to the simple linear regression model, where the basic model involves an equation of this kind, okay, where y, my dependent variable, okay, is an observable variable, and x1, my independent or explanatory variable, is also an observable variable. Okay, so you saw several examples of this. In the first example, y was wage, x1 was education. In the second example, y was price of a house, x was its size. In the third example, y was CEO salaries and x was return on education. Each of these are random variables, and these are observable, which means that I can pick up data and I can actually see these variables as data. Now, so that's so far as the dependent and explanatory variable is concerned. Now, what about alpha and beta? These are just the counterparts of the y is equal to mx plus c that I was talking about, right? So when you are estimating a two variable model, what you are doing is you are setting out to say that, look, there is a straight line relation between y and x, but I know neither I know neither the intercept of that straight line, nor do I know the slope of that straight line. I will have to estimate these. Okay. So I start by getting some data on y, some data on x, and I use that data to estimate the slope and the intercept, where the slope and the intercept in the two variable model are denoted by alpha and by beta. So I will repeat this once again. Our basic model is all about estimating alpha and beta, where alpha and beta are simply constants which are unobservable. I can't see those constants, so I have to estimate those. So I start with some data and then I use two variable regression as follows, as I'm just going to go on and explain. Now, before I proceed, look at one more term, which is this term U, okay? So U is also known as the error term, okay? These are the errors. Now, what's with the errors? Look, what is being told to you is that, look, there is a straight line relation between y and x, but it's not a perfect relation. It is a relation which can be disturbed. What does that mean? It means that even if I have fixed my x, I still may get different values of y. All right. So let's say, let me talk about this in the context of the wage education example. Even when I talk about a person with exactly 10 years of education, right? I'm going to see that everybody in a collection of, let's say, 30 people who have 10 years of education, they are going to be earning different wages. Not everyone with 10 years of education will be earning exactly the same wage. Okay. Now, let me repeat that. So what I'm saying is that you have a relation between wage and education. But the relation is not an exact one. If there was an exact relation, then you would simply have y is equal to alpha plus beta 1 x1. So anyone with 10 years of education would be earning alpha plus beta 1 into 10 as wages. That doesn't happen, okay? In reality, even when you fixed x and you said that x is equal to 10, you're going to find not one y, but you're going to find many, many, many y's, which is to say that people who have exactly the same x, exactly the same years of education, will actually have different wages. How do we capture this in our model? We capture this in our model, in our simple regression model, by incorporating what we call an error term. What is this error term? The errors are unobservable random variables, okay? So we know they're random. So sometimes you'll see that people with 10 years of education are earning a lot, okay? Which means U is very large. And sometimes you're going to see that people with 10 years of education are earning very little. So in this case, U is actually very small, right? So you're actually going to have some sort of an average. So you're going to have some sort of an average wages for people with exactly 10 years of education, and there's going to be like a lot of fluctuation around that average. Okay, so let me just show you a picture, and then I think this point may be a little clearer. Okay, so here. So this is the picture that I wanted to show you. So what I'm saying is that you have yeah. So I have over here x, which is my explanatory variable. Let's say x is education. And I have over here y, which is my dependent variable. Let's say these are wages. Okay. Now, these are actual observations. So, so what these represent are different wage education combinations, right? Now, when I'm running a regression model, what I'm saying is that I'm going to estimate a straight line that best captures the relation between y and x. Now, look at one thing over here. If I want to estimate a relation between y and x, which goes through all the actual observations on y and x, I will not get a straight line. So let's say this is the data set that I showed you on wage and education. Let's say this is a plot of that data set. Each of those points represent that plot. If I want to draw something that runs through all of these points, then as you can see, I'm not going to get a straight line. I'm going to get something like this, which is not a straight line, right? So what's the other way of looking at this? If I want a straight line, as I have over here, if I want a straight line to approximate the relation between y and x, obviously it's not going to go through all of these points, right? Some of the points may be, so some point may be on top of the line, but mostly the points will be off the line, as you can see, right? So what exactly does that mean? Well, first of all, this should be telling you a lot about the errors, okay? So even when, let's say, I have fixed my x, I see that there is, so this is the actual wage of a person with X years of education, right? But compared to the average wage that a person with X years of education earns, this person is earning a lot more. Let's take another point. So what am I talking about? Look, I'm saying that, let me just repeat this once. So I'm saying that here you have some data. You have some data on X, you have some data on Y, and you're using two variable regression model. When you're using the two variable regression model, you're actually trying to estimate a straight line, which best captures this relation between Y and X. And whenever you're drawing such a straight line, it actually captures the relation between the average value of Y and X, and it looks like this, right? So the line does not pass through all the points, number one. Number two, some of the points will be lying above the line, some of the points will be lying below the line, right? And some of the points may lie on the line, right? In each case, let's see what it means. So for someone with X1 years of education over here, right? This point represents the actual amount of education that, so this is education. So someone with X years of education, this represents the amount of wage that he earns. Now, as per my regression line, this is the average wage of such a person. So the actual wage is higher than the average wage, indicating that there is an error which is positive. Let's look at another example, as in this case, where a person is has X1 years of education and the actual point is Y1. So he's earning this amount. As per our line, he should be earning this amount, right? If this is not visible, let me clear the ink and let me start again. Yeah. So if someone is has X1 years of education, he actually is earning Y1, but our line indicates he should be earning this much. So he's earning this much less. So in this case, again, we have U, which is negative. And so you can have some points like this, which are below the line, some points like this, which are on the line, where this is my line, right? So the point of all of this is to really tell you why you have an U. The U term in your regression really captures that you can have errors which represent that some dependent variables will be over and above average, and some will be below average once you had treated the X as though it were fixed. Okay, right. So with this background, let me quickly take you to how you actually estimate this line. Okay, you use something called the method of least squares. Okay? Now, what is this method of least squares all about? Very quickly, I'll just tell you what it's all about and then go on to show you how it works. So the method of least squares is all about fitting the best line. As I said, here you have a scatter of the relation between y and x, right? Now, if you want to cover all the points in the scatter, you can't have a straight line. So if you want a straight line, some points will be off, some on the scatter. How do I choose the best line, right? We choose the best line using the method of least squares in the following way. We look at these gaps. We look at the distance of the points from the line, and then we minimize these distances. Now, if we were just to add these distances, all of them, if we want to minimize all of them, we have to add all of them. If we were to just add all of them, some would cancel out, right? Some of the positive and the negative distances would cancel out. So what do? We square them. We square them, and then we add them, and then we minimize them. Minimizing the distances gives us the best line. What does that mean? What's the best line? So the best line is one which has the best intercept and the best slope. That's what it is. And that's what least squares does, okay? It chooses the best intercept and the best slope. From a discussion about straight lines, you've understood what a straight line is all about. It's all about an intercept and a slope. So choosing the line of best fit is basically about choosing the intercept and the slope that minimizes the sum of squared residuals or the sum of squared distances of points from this line. Okay. So just one more point before I show this to you technically. So you see, I could have drawn many lines. Many lines could have been drawn, right? All these lines have different intercepts and different slopes. When we run a regression model, we are using the method of least squares. That's what a regression model does. It uses the method of least squares to actually choose the line which is the line of best fit. Okay. So I just take you a bit of technical details on this, and then we will see this with some data. We're going to look at the assumptions based on which the ordinary least squares regression model stands. All right. So just bear with me as I take you through some technical details regarding what I call the OLS methodology. So when we are using the simple linear model, we are actually we are actually working with this particular model, right? Y is equal to alpha plus beta x plus u. where y is the dependent variable, x is an explanatory variable, y and x are both observable, and u is a random variable which is unobservable, and alpha and beta are constants which are unknown. So that is the intercept and the slope that we do not know, which we have to estimate. How do we work with this? We use a random sample of observations on x and y. We use some data of the kind I showed you. And we use the method of least squares, which involves fitting a straight line of the sort y is equal to a plus bx to a given scatter of observations, to the kind of scatter that you just saw, right? Now, as I said, the method of least squares involves minimizing the sum of square deviations from the line of best fit. Deviations of the actual observations from the line of best fit. So here is my actual observation yi, and here is my line, which is a plus bxi. So remember, I'm trying to fit a line of this sort. So I will try to minimize these deviations, right? Y minus, so y is the actual, and so this is yi minus a plus bxi. So when I open the bracket, it's yi minus a minus bxi whole squared. So these are the sum of squared deviations. Now, from basic calculus, you should know that a minimization procedure involves taking the partial derivatives and equating it to 0. So I'm minimizing the sum. So this is the sign for sum. I'm minimizing the sum of squared deviations, and I proceed by equating the partial derivatives to 0 and then solving. So when I solve, I get y star, I get a star, which is my intercept, my best intercept, and b star, which is my best slope, right? And how do I get those? So to Dr. Pandey, who asked those questions, how did I get that intercept and the slope? So when you have some data on y, you have some data on x, and you've used regression, what you've essentially used are exactly these two formulae, okay? How did I get the intercept? I simply looked at the average dependent variable minus b star into the average explanatory variable. And what is b star? So b star is sigma xi minus x bar into yi minus y bar upon sigma xi minus x bar whole square. So if you see, on top you have a covariance and below you have a variance. So on top you have the covariance between x and y, below you have the variance of x. Okay, let me repeat. So you have a context. You are a labor economist who wants to find out the relation between wages and education. You want to ask, as a person gets more educated, do they earn more? So this is the context. From that context, I use some data on the dependent variable, which is wage, and the independent or explanatory variable, which is education. Now, I use least squares regression. What does that mean? It means that I'm using a method to estimate the best straight line relation between wage and education. Okay. Now, whenever you are using least squares regression, what are you doing? You are using the method of least squares to fit a straight line to the given data that you have on wage and education. Okay. And how is that straight line getting generated? It is getting generated by the method of least squares minimizing the sum of squared deviations of the scatter from the line, and then choosing the line that best fits this data, where best is the intercept and the slope, which minimizes the sum of squared deviations of the scatter from the line. And how do you get that? You get that exactly from what you can see on your screen. So the formula for the intercept is y bar minus b star x bar, where b star is the least squares slope estimate. So you will get the slope estimate by looking at the covariance between x and y, dividing that by variance. And we get the intercept by simply using this formula. Average value of dependent variable minus the estimated slope into the average value of the explanatory variable. So every time that you are using least squares, no matter in what package, whether in Excel, whether in SPSS, whether in Stata, whichever package you are using, whenever the package returns a slope estimate and an intercept estimate, this is the way that slope and that intercept has been calculated. You can check that. Okay. All right. So we call these the OLS estimators. So just a quick moment, I'll take you back to my regression model. My regression model is this one, right? Dependent variable y, explanatory variable x, slope is beta, intercept is alpha, I don't know what it is, which is to say I have data on wage, I have data on education, but I don't know what is the straight line that best describes it. Okay, so I'm going to use regression. I'm going to use OLS to estimate alpha and beta. Now, when I'm doing that, what I'm doing is basically, as I just described, fitting a straight line and obtaining estimates of the unknown parameters alpha and beta using the following estimators. Okay, what are the estimators? So these are the estimators. An estimator is basically an equation. All right. So again, Dr. Pandey, to answer your question, you had asked how did we get that slope? How did we get that estimate? We got that slope and we got that intercept precisely by using these formulae. Okay, these two that you can see on your screen. So we estimated the slope beta, and we call the estimated slope beta hat using this equation, which is the OLS slope estimator, and we estimated the intercept by using this equation, which is the OLS intercept estimator. Okay, all right. So I'll just run you through the OLS assumptions, and then I'll take some questions. Now, I know it's almost 1:30, but we started late. So can I go up to 2 o'clock? Anjali, will you please let me know what is the time I have?
Ma'am, you can take another 15 minutes, 20 minutes, not an issue, ma'am.
Okay. So I'll try and take another 15-20 minutes. So
okay, ma'am.
Okay. So look, guys, let me take you through what I planned to work on. I'm going to be back tomorrow. So if there are questions that remain unanswered, I will start tomorrow's session by first answering those questions. So don't worry about your questions not being answered. Okay, so let me just take you through what I have in the next 15-20 minutes that I have, and then I'll take some questions today at the end.
Ma'am, it's okay. Ma'am, you can concentrate on your lecture. Dr. Anshika is combining all the questions, and at the end of this session, she'll compile all the questions and ask some common questions so that majority are being asked, ma'am. Okay, thank you, ma'am.
Wonderful. Okay, so then I'll just concentrate on doing what I'm doing. Okay.
Yes,
right.
ma'am. Dr. Anshika is on a lookout. She's compiling all the questions and will ask the common questions, ma'am.
Wonderful. So I'll take questions at the end once Dr. Anshika, who's compiling the questions, has compiled all of them. Okay.
Yes, ma'am.
I'll just
Yes, ma'am.
get back now to my slideshow and yeah. Right. So if you remember, we were discussing the basic model, and I just told you how using OLS we actually estimate alpha and beta, which is the intercept and the slope of this line, which best approximates the relation between y and x. Okay. Now, let me take you through some of the assumptions of the OLS model. So this model is actually resting on certain assumptions. What are those assumptions? First, we assume that there is a linear deterministic relation between the average value of y and x1. Now, y I told you is a random variable. So when I'm talking about its average value, I will talk about its expected value. Okay. So the expected value of y is nothing but an average value of y. Okay. Because y is a random variable. So the first assumption of the linear regression model is that there is a straight line relation between the average value of y and x. The straight line having the intercept alpha and the slope beta, neither of which we know, both of which we will estimate. Okay, so alpha, beta are just constants. They're just numbers that are unknown. Now, remember my model, quickly to take you back to my model. My model is alpha plus beta x plus u, right? So a lot of my assumptions are going to be about the errors or the u, which are unobservable. That is why I need the assumptions. Okay. So what all am I going to assume? I'm going to assume that the errors are zero mean. Okay. Average value of the errors are 0. Second, they are homoscedastic. What does that mean? You know, we are very fond of big terms. So first of all, it's a big term with a simple meaning. It simply means that the errors have constant variance. All right. So whether I'm looking at the first error, second error, third error, fourth error, doesn't matter. All the errors have the same variance. Remember what they are. The errors are random variables. They are not observable. That's why I have to make assumptions about them. I'm assuming that each of these random variables, okay, these errors, they have zero mean and they have the same variance. Putting that in a slightly fancy way is the errors are homoscedastic and zero mean. Now, the errors we assume are identically and independently distributed, which means we are assuming that the errors the errors have zero correlation among themselves. No two errors are correlated. Okay, what else am I assuming? I'm assuming that x is a variable. It is not a constant. Okay, not a constant. Very important. So my dependent variable is y, explanatory variable is x, and x has to be a variable. All right. If it's just like 10, 10, 10, 10, 10, or 5, 5, 5, 5, 5, that doesn't work. X can't be a constant. We have to rule it out by assumption. All right. We are also assuming that x is uncorrelated with the errors. So very important. So just to take you back to the model once again. So here we are saying that, look, y has two parts. All right. Y has a part which is dependent on x. That is this part, alpha plus beta x1. Right? And y has another part here, u, which is the errors. And we are saying that, look, these two parts are watertight. They are not correlated. Okay. So my regression model is splitting y into these two distinct parts, where this I'm going to call a deterministic part, okay, and this is a random part. Now, why am I calling this the deterministic part? Because once I know X, I can actually say that Y is alpha plus beta X1. That's the deterministic part of Y. And the error part of it, remember the errors are unobservable, are just random. So we are making a lot of assumptions about those. They're zero mean, they're homoscedastic. And one more of our assumptions is that X, which is a variable, all right, is not correlated with the errors. Very important. Because you see, if they are correlated, then you're not even splitting Y into two parts. That's the point. So to split Y into these two watertight parts, the X part or the deterministic part and the error part have to remain uncorrelated. Okay. What are my other assumptions? My other assumption is that the errors are normally distributed. So I hope you see that so far as assumptions are concerned, who is the hero? The hero is your errors, right? All the assumptions, maximum assumptions are about the errors. Why? Because they are unobservable. So because we can't see them, we have to make many guesses about them. And that's what these assumptions are all about. So another assumption is that the errors are normally distributed. This is a classical assumption which is necessary for hypothesis testing. Without this, you cannot do hypothesis testing. Okay, so that is the way the model assumptions play out. All right. Okay. Now, I'll quickly take you to some types of data which are typically used in regression models, and then I'll show you some results which I have run for you. Okay. Now, broadly, the kinds of data we will be handling, that I will be handling in this lectures today and tomorrow, are cross-sectional data sets. Now, you have on your screen a cross-section data set. Where you have 526 observations on 526 people. On how many variables? On 1, 2, 3, 4, and 5 variables, right? So this is a cross-section data set where the entire variation in my wage variable is coming out of variation across individuals. Do you see that? Look at the column wages, right? This is the wage of the first man. This is the wage of the, this is the wage of the first woman. This is the wage of the second woman. How do I know this is woman? Because I have a variable called female, which is 1 for women, 0 otherwise. Okay. The third observation pertains to a man because this is 0. So if you look at this column, if you look at the column of wages, do you see it's not a constant, it is a variable. This is my dependent variable in a cross-section data set. Why is it called a cross-section data set? Because the entire variation in wage is coming due to variation across cross-sectional units. I don't see a constant because the people are different. Okay. As opposed to this, let's see a different kind of data set, which is a pure time series data set. Okay. So I hope what a cross-section data set is clear. This is an example of a cross-section data set. This is the data that I have actually shared with you also. All right. So here is another cross-section data set, which is a cross-country data set, where you have data on 61 countries, on GDP growth, and on some other variables. Why cross-section? Because the entire variation is due to the fact that we are looking at different countries. As opposed to this, let's see a time series data set, which is this one. So here, I have data for a country called Puerto Rico. I have data with 38 observations from the year 1950 to 1987. So look at one of the variables, which is unemployment. This is the unemployment rate. Okay. Now, the variable I've circled is actually the dependent variable in this data set. So the unemployment rate, as you can see, takes different values. Why is it taking different values? It's taking different values because the period of time is varying. So the variation in Y is entirely due to the passage of time. This is a pure cross section. Sorry, this is a pure time series. Okay. So the difference between a time series and a cross section has to do with what is it that generates the variation in my variables. There are other kinds of data. We'll talk about those tomorrow. Let me now show you some regression results which were run in Excel. Okay. All right. Here we go. Right. So I have shared several data sets with you, and one of the data sets is called wage data. So this particular regression was run using wage data. So here is the data. I've just highlighted the two columns. This is the data, and I'll show you how to run the regression in just like 5 minutes. Okay. Now I ran the regression in Excel, and this is the Excel output. Let me take you through the Excel output very quickly. Now, Anjali, let me just interrupt and ask you, how much time do I have from now?
Ma'am, another 10 minutes, ma'am.
10 minutes. Okay, fine. I'll just look at that. Okay. All right. So I just showed you the data. An excerpt from this data was shown to you in my PowerPoint slide. When I ran this regression in Excel, look at what it is giving me. All right. So let us zoom in and look at some of the results. First of all, here it is giving me an intercept. Do you see? I have highlighted the intercept, and I've just put it in blue. Remember, intercept blue and slope is red. Okay. So this is exactly, so what are we doing? I have run the regression in Excel. I'm taking you through the regression output. The first thing in the regression output to note is the estimate of my intercept coefficient and slope coefficient. And here they are right here on your screen. So the intercept is minus 0.90, the slope is 0.54, which is saying that an extra year of education increases wages by 0.54 dollars, or by about 54 cents. Why am I saying increases? Because the slope has a positive sign, right? If it had a negative sign, then the story would be different. Then I'd say it is decreasing. But in this case, as we expected, more education increases your wages. So this is part of the output that I would like you to see. Now, look at some more bits of output. Now, look at the column that I am now highlighting. I'm just highlighting, 17 observations in this column, and I'm just, highlighting them in gray. All right. These are predicted values. Now, guess what the predicted values are? So you can see these predicted values right here. All right. The predicted values are values on the line. How do you get the predicted values? Okay. You get the predicted values simply by using the slope and the intercept. Okay. So let me show you what Excel has done here. So if you can see the plot that I have on the screen, all right, Excel has estimated a regression line, which is indicated by this yellow, which is indicated by these yellow points. It has not actually joined the line, but it's showing that there is this straight line where we have the following data, which is indicated in blue. Okay, so please look at this diagram very, very carefully. Along the x-axis, I have years of education. Along the y-axis, I have wages. Okay, so here are wages, and here is education, and here I have indicated in yellow. All right, I have the regression line, right? Now, when we are talking about predicted values, we are actually talking about these points, right? How do we get these points? These points can be obtained simply, as you can see, by using the slope and the intercept in the following manner. I'd actually like you to make a note of the fact that the slope is 0.54 and the intercept is minus 0.09. Okay. Now, let's look at the first observation in our data set. Okay. Our first observation is 3.1. That's the dependent variable, and wage regression line. Look at a positive residual in this case. My model is saying someone with 18 years of education should be earning about $9.63, but person is actually earning more. He's earning $11. So I get a positive residual. Okay. So the residuals are a kind of approximation of your errors. Remember, the errors we cannot see. But once we have run a regression, we've got the residuals. Now we can actually estimate the errors. Okay. So I'll stop here for today, and tomorrow I'm going to start with the multiple regression model. I'm going to tell you how to interpret coefficients in a multiple regression model, and then we look at hypothesis testing in the context of a multiple regression model. Exactly the same way as in a simple regression model. There's no difference in how you do a hypothesis test. Okay, so that's what we will look at, and the remaining issues I could not touch on today, R squared, etc. I will touch on tomorrow. Before I finish and take questions, just one more thing: how to run a regression in Excel. To run a regression in Excel, what you need.
And the question has already been answered by Professor C.P. Gupta in the chat box. Sir is simultaneously answering most of the questions.
Okay. So then I can finish off now.
So, ma'am, I'll just request Dr. Anshika to ask any compiled questions which have not been asked. Dr. Anshika.
Ma'am, there was questions. I am taking questions from the Q&A section.
Anshika, can you please be loud?
Yeah.
Ma'am, am I audible now?
Yeah, you are not visible.
Ma'am, my video is paused. I'm unable to. The host has paused my video.
Anshika,
fine.
I can hear you.
Ask the question, Anshika.
I'm taking questions from the Q&A sections.
Yes.
There is a questions like difference between regression and correlation.
Okay. You just tell me the question, I'll answer them at one go. So what is different? I'm noting down the questions. So difference between correlation and regression, okay?
Ma'am, next is why only straight line, not a... Why can't we explain a relation without a straight line?
Okay, what else?
Ma'am, next is, does regression model affected due to unforeseen happening?
Okay, all right.
Or will it remain constant?
Okay, all right, fine. What
for
else?
example, GDP with production in manufacturing sector.
Okay, fine. Yeah, I see the question. Fine.
Next is, ma'am, which statistical package is good for analysis?
Okay, so Anshika, let me divide the questions into conceptual and others. So these are conceptual questions. Are there any other conceptual questions?
Ma'am, students are also asking about random variables and how can they improve the regression model.
Okay. Anything else?
Accurate way of finding the line of best fit. They want to understand that.
Okay.
And questions like the difference between alpha beta and alpha beta het,
Okay.
and
All
the difference between estimator and estimate.
okay. Great. Great. Okay.
And ma'am, sorry to interrupt the participants and asking again and again for a demonstration of use of regression in Excel, sir, ma'am.
Sorry, they're asking again for what?
For demonstration of use of how to use regression in Excel, ma'am.
Yeah, I just showed that. I was just going to show that, Anjali. Can I just show that first?
Ma'am, please, ma'am.
Yeah,
Teacher
okay.
has given the answer on chat box.
Sorry?
Okay, they
Teacher
want a
has-
demonstration. I'm getting repeated thing. Professor C.P. Gupta has given an answer in the chat box, but still they are asking for a demonstration, ma'am.
I'm just doing, I was
Yeah.
just going to do that actually, Anjali. So I'll just do that, okay?
Okay,
So,
thank you, ma'am.
so I will, you know, I'm sorry if I'm delaying your lunch, but due to this little, this thing.
No, ma'am,
we
it's
got to get-
okay. You can continue, ma'am. It's not an issue, please.
Not an issue. Okay, thanks. So I'll just start by showing you how to run a regression in Excel, and then I'll take up your conceptual questions. Okay. So Anjali, please tell me when to stop. All right. Okay. All right.
Ma'am, you take up all these questions and then we'll stop, ma'am. Okay.
Now, all right. All right. So now, can all of you see my Excel screen? Now, here I have some data in Excel. Okay. Right. So here is this data that you can see on my screen. This is the data in Excel. Now, I want to run a regression. How will I do that? I go to data. Okay. Now, sorry. Oh dear. Hang on. Just one moment. Right. So I go to data and I see that it is not showing data analysis. So what I'll have to do is I have to add in the analysis toolpack. So if your screen is not showing an option called data analysis, just in case as mine is not showing, all right, we will add in data analysis toolpack like this. We will go to file, we will go to options, and then we will go to add-ins. In add-ins, we will go to manage Excel add-ins and add in the analysis toolpack. So I've selected analysis toolpack. Now I say go. So it will give me this kind of an option and I will add in the data analysis option. So now it is showing me data analysis. I will repeat this once again. How do you add in the data analysis option if your Excel is not showing it? First, you go to file. Okay. Then you go to options. Okay. Then you go to add-ins. Once you are in add-ins, you will click analysis toolpack and then below here, you will click on go. Once you do that, it is going to install the data analysis toolpack for you. Now, how will you know that it is done? Once it is done, this option, the data analysis option will show up. Okay. All right. So once you have done this, just save it. So I'll now show you how to run a regression in Excel when you have the data. Now, all of you have this particular data set that I have opened. It is the wage data file that I am now opening on my screen. So you can also open this wage data file now on your screen. Open this file in Excel, install data analysis if you don't have it already, and now click on data analysis. Once you do that, it's going to give you all these options that you can see. One dialog box opens like you can see on the screen. Now here, you just scroll down till you see regression. So you click on regression, you say, okay. Now, once you do that, it's going to open another dialog box like this, where it's asking you for input Y range, followed by input X range. Y is the dependent variable. So first you select the dependent variable. You simply click on the dependent variable, everything with the label, and then you select all of it. All right, so it has been selected. Dependent variable has been selected. Now you give the X variable. Again, you go to, you click on the X variable, select the whole thing. This has also been selected now. So the first step about running the regression is to select your Y and select your X. Okay. Then ask for labels. If you ask for labels, it will use the data titles to label your regression results. All right. Next, note that this option is already there. New worksheet apply. It means that your results will be shown on a new worksheet. You can ask for residuals. I have asked for residuals, and I have asked for residual plots. You can ask for all this and then click OK. There you are. Okay. So you could also have asked for one more thing. So I just repeat this. Okay, I just repeat this. So running a regression in Excel. Open the data set, go to data analysis, install data analysis if you don't have it already by going to add-ins. Okay. Go to data analysis, click on regression, select the data. So all the data, so your Y has been selected, your X has been, I will just select the X also. You just select by clicking on the data. You ask for labels, ask for the output on a new worksheet, ask for residuals, residual plots, and also a line fit plot. A line fit plot will also give you the regression line. Okay, and then you go okay. There you are. So this has given me the regression results. You can see these are the regression results. This is the residual plot, and this is the regression line or the line fit plot. Okay, so yellow is the regression line, and the scatter is shown in blue. All right. So this is how you run a regression in Excel. Is there any question on how to run a regression in Excel? Should I repeat this, or should I now take the conceptual questions? Please let me know. Should I repeat how to run a regression in Excel?
It is clear to all participants.
Ma'am, it's clear, not required.
Okay, great. Fine, fine. So then I'll just now take your conceptual questions and I'll try to answer them as, sorry, yeah, so I'll try to answer those now. Okay. So one of the first questions is about correlation versus regression. Regression is a much more powerful tool than correlation, especially when you are talking about multiple regressions. When you are talking about two variable regressions, um, correlation tells you whether there is association between two variables. It gives you strength and sign of that association. Regression takes you one step further. It allows you to talk about marginal effects. It allows you to answer the question that if my dependent variable, if my independent variable changes by a little bit, how does my explanatory variable change? So clearly regression adds much more knowledge than correlation. The second thing with regression, you can do hypothesis tests. You can actually check whether there is a significant, statistically significant relation between X and Y. What that means, we will start with what that means tomorrow when we talk about hypothesis tests. All right? Okay. So that's the first question about correlation and regression. Now the second question, is straight line my only option when I'm running a regression? Now, okay, please understand here that your question is yes and no. Okay, why yes? Every time that you're using regression on two variables, always you can only estimate a straight line, nothing other than a straight line. That's the yes. Straight line is your only option. Okay. However, does that mean that I can only look at straight line relations between y and x? No. Answer to that is no. So just think over what I have said. You see, I can run a regression between y and x. I can run a regression between log y and x. When I'm running a regression between y and x, straight line. I get a straight line. When I'm running a regression between log y and x, again I get a straight line. But straight line, what is my dependent variable now? My dependent variable now is log y. It is not y. All right. The minute you say log y is equal to beta x, what are you saying? You are saying that y is equal to e to the power beta x, which is a nonlinear relation. So, do you see the yes and the no? Yes, every time you run a regression, you get a straight line. The straight line can be between y and x. The straight line can be between log y and x. So when the straight line is between log y and x, the underlying relation between y and x is nonlinear. Because then y is equal to e to the power beta x. Okay, so we will talk about this when we talk about models with alternate functional forms. The basic deal here is, again, regression is very powerful. You can accommodate a whole bunch of a whole bunch of non-linearities within this linear regression model. And a point that is linked to it, let me just emphasize this right here. If you look at my slides, I had mentioned something here. I had said that our model is linear in parameters. What does that mean? It means in my model, always beta will be to the power 1. I will not look at models where beta is to the power -1, or let's say root beta, or 1 upon root beta. Those are out. Those kinds of models where the parameters are in some sort of nonlinear format cannot be fit into the rubric of your simple regression model. So to come back to this question of is it only straight lines? Yes, it is only straight lines, number one. Second, the model is linear in parameters, which means beta will always only be beta, no square root, etc. Third, but a whole bunch of nonlinear relations between y and x can be fit into this framework by cleverly using logarithms and other formats, which we will look at tomorrow. Okay. Now the question about the regression line, is it stable? Does it change? Yeah, sure. The regression line is you get one line for one data set. If the data changes, the line changes. So if you're using time series data to estimate the relation between GDP and productivity, using data from 1960 to 1980, you will get one line. The line is going to change once you update your data set and you say, I'm now looking at data from 1960 to 2000. Clearly, the stability of the line is driven by the underlying data. Data changes, line changes. Okay. All right. Now, the best fit methodology, there was some question on that. How do you get alpha hat, beta hat? And what is alpha hat, beta hat, right? Very quickly, I'll come to those because both of these questions are linked. And linked to that is a question of what is an estimator and what is an estimate. So I will take all these questions together. Let's start with how do we get this straight line? I will jump to my notes and just take you through it here. Sorry. Yeah. So you get this straight line by minimizing this character. What is this character? So you have this actual data set, right? You have the actual y's. And then you have a line. So when a y is on the line, I can call it a plus bxi because my line is vxi. So what am I doing? I am trying to fit a line y is equal to a plus bx to some data. So how do I proceed? I proceed by minimizing the sum of squared deviations. I'll show you the picture in just a bit. So the deviations of the actual data points from the points on the line, which is a plus bxi, I take the difference, I square it and minimize it. Minimize it with respect to what? With respect to the intercept and the slope, right? So you minimize this sum of square deviations and you optimally choose the slope and the intercept as per these two formulae, right? If you actually minimize this expression and you work it out, you are going to get exactly these two formulae. All right. This is what you get when you minimize. You know, when you equate del z del a equal to 0, and this is what you will get when you put del z del b equal to 0. You're going to get this. This is how you choose the line of best fit, which is basically about choosing the right intercept, the best intercept, and the best slope. Now, let's come to the alpha hat and the beta hat. I hope the question about how you choose the line of best fit is clear. So what is alpha and beta? Alpha and beta have to do with my dependent and explanatory variables y and x. Here is y and here is x. Y dependent, x explanatory. I am trying to capture the relation between the two. I know there is a relation. I know there is an intercept. I know there is a slope. I don't know what they are. The unknown numbers, the unknown slope, the unknown intercept is alpha and beta. That's alpha beta. Enter the hats. What are the hats? The hats are the estimators. What are the estimators? The estimators are the equations. What are the equations? The equations are the equations for calculating the line, calculating the slope and calculating the intercept using the method of least squares, right? So here you go. So what is your beta hat? This is your beta hat. Your beta hat is simply covariance of x and y upon variance of x. So beta is a number I don't know. Beta hat is my estimator or the equation to calculate or to get an estimate for this unknown beta. Alpha hat is y bar minus beta hat x bar. Okay. So alpha hat is simply the formula, the equation that I use to estimate the unknown intercept, okay, which is y bar, so how do I get that? It's the average value of y minus beta hat into the average value of x bar. So for the person who wants clarification on estimator versus estimate, these are alpha hat and beta hat are the least squares estimators. Is that clear? Their equations. And you can see their functions of x and y, right? So alpha hat and beta hat are right here on your screen. They're functions of x, they're functions of y. X and y being random variables, alpha hat and beta hat are also random variables. These are the OLS estimators. So estimators are equations, estimators are random variables. Make a note of that. Now, let's cut to estimates. What are the estimates? I'll show you the estimates on my Excel file. You see, once you have used a regression model, you obtain estimates. I have just highlighted these estimates in yellow on my screen. So 0.90 is my estimate of alpha using alpha hat, which is the estimator. 0.54 is my estimate of beta using beta hat, which is my estimator. So all three things are kind of hanging there. There are these unknowns alpha, beta. They're the unknown parameters in my model. That's what I set out to estimate. There are these estimators that I use to estimate them. Excel has used the estimator y bar minus beta hat x bar to calculate alpha hat, and the estimate is minus 0.90. Excel has used covariance of xy upon variance of x to calculate beta hat, and the estimate is 0.54. So you see, estimate is sample specific. If I change the data, the estimate changes. Estimates are the numbers that I get as estimates, using my estimators for a particular data set. So I hope the distinction between estimators and estimates is clear, okay? And I also hope that the difference between alpha hat, alpha, beta are also clear. How do I improve my how do I improve my regression? Look, a surefire way of improving your regression is to add more variables. So you can see right here, I have highlighted in yellow on my screen, the R squared of my model. Tomorrow, I'll discuss this a little more. So the R squared is a verdict on your model, which is telling me that only 16% of the variation in wages is explained by variation in education, which is not good news. So I can improve on my regression model for one by adding more explanatory variables, which would take us from simple regression. From simple to variable regression, it will take us to multiple regression. Okay, so I'll take that tomorrow. Okay, we'll start with that, and I think Professor Gupta is also here, so I'll also discuss with him on what other points we can cover and the sequence in which we can cover them. Just let me know if there are any other questions which I've left unanswered and which I can maybe respond to right away. Then one thing about the book. The book that I like to recommend, there are these two books which I like to recommend. One is the book by Woolridge. I share the reference with Anjali via email so that you can all have access to it. So one is a book by Woolridge called Introductory Econometrics. The second reference that I like to use is a book by Dougherty, Christopher Dougherty. Dougherty. So Woolridge and Dougherty, both are introductory texts in econometrics, are the two books that I would like to recommend. So that's so far as the books. There was a question on random variables. I think this concept was covered earlier in your FDP, this one, what is a random variable? So I suggest you just revise that concept. and I'll take, if some questions can be shared with me overnight, I can have another quiz. I'll try and respond some more, then I come tomorrow. Okay?
Ma'am, we'll share the email ID of yours, ma'am. Later on, any questions that participants are having, they can always mail you the questions so that
Yeah,
they
so
can
if
be
you,
answered later on also, ma'am.
right, if you could just share, yeah, sure, that's great. Yeah, great.
Ma'am,
Great.
we'll share, we always share the mail IDs of all the resource persons at the end of the FTP. We'll do that, ma'am.
Okay.
Definitely.
Right. So
Yes.
is this, I hope I've been able to answer the questions, and there
Yes,
is
ma'am.
also a time
Majority of them, ma'am. It's
Okay.
okay.
Thanks.
May I request Dr. Anshika?
Yes, ma'am. Yes, ma'am. Thank you, ma'am, for such a wonderful session.
Anshika, voice.
Ma'am, is it audible now?
Yeah, yeah.
Yes. Yes.
Thank you, ma'am, for such a great session, for explaining the concepts of OLS regression in a very simple and easy way with diagrammatic presentations and examples and softwares. It's really interesting to listen to you regarding the assumptions, predictions, and a lot more. You have answered most of the queries in a very detailed manner. Hope to that participants are also happy about it. I'm sure they are definitely happy about it. Thank you, ma'am. It's a privilege to have you here.
Not at
Thank you,
all.
ma'am.
Delighted. I mean, I'm hopefully, we are learning online things, so not perfect, but we'll get there. Okay.
No,
Thank
ma'am,
you.
it was a
Bye-bye.
perfect presentation, ma'am. No
Okay.
flaws at all, ma'am. Thank you, ma'am.
Okay. Thank you. Thank
Thank
you.
you.
Bye-bye.
Thank
Bye.
you, ma'am.
Bye.
Bye.